Okay, hello, welcome to today's lecture. We are on chapter 7. Let us continue 7.3. And remember that our midterm 1 is on Sunday, 2 to 4. So let us review what we learned so far. We learned about hyperbolic functions. Review. Hyperbolic functions. So first of all, we defined hyperbolic sine hyperbolic x, which is defined as e to the x minus e to minus x divided by 2. Then we define hyperbolic cosine e to the x plus e to minus x divided by 2. Then by dividing sine over cosine, cosine over sine, we have hyperbolic tangent and hyperbolic cotangent. Well, we also learned about the derivative and integral of these functions. So let's write them down here, important ones. So let's start by taking the derivative of hyperbolic sine, which is equal to hyperbolic cosine. Then the integrals, since we know that the integral and the derivative are opposite of each other, it means that if you take the integral of hyperbolic cosine x dx, it must be equals to hyperbolic sine. Next one, the derivative of hyperbolic cosine is equal to hyperbolic sine. What's the meaning of that? It means that if you take the integral of hyperbolic sine, it must be equal to hyperbolic cosine. So the integral of hyperbolic sine dx is equal to hyperbolic cosine. Some more formulas for you. The integral of, let us talk about secant. Hyperbolic secant squared of x dx is equal to hyperbolic tangent plus constant of integration, so don't forget this, constant of integration. Then the integral of cosecant, hyperbolic cosecant squared of x dx is equal to minus cotangent hyperbolic plus constant of integration. And the two important ones, if you see the product of secant and tangent, so if you have hyperbolic secant, hyperbolic tangent x dx, it is equal to minus hyperbolic secant x plus constant of integration. And finally, if you have the integral of cosecant, cotangent, hyperbolic cosecant, hyperbolic cotangent x dx, this guy is equal to minus cosecant hyperbolic x plus constant of integration. Okay. Last time we went over some examples. Let's continue. We are on page 3 of 7.3. So we're done with A and B. Part C says, find the integral of cosecant hyperbolic of square root of x divided by square root of x dx. Well, so here you have hyperbolic cosecant, and instead of having x, we have square root of x. Let us use u sub. So let u be square root of x. Our goal is to substitute using u sub, a new variable like u. So du is equal to, we take the derivative of left-hand side and we take the derivative of right-hand side. Here you have x raised to a half, so here you get 1 over 2 square root of x dx. Take a look at this integral here. On the denominator, you have square root of x. On the numerator, you have dx, dx, square root of x, square root of x. So if you multiply and divide by 2, you can actually form your du. So this integral is equal to the integral. You can write 2 outside the integral. It won't change the integral. So you get hyperbolic cosecant square. And instead of x, you're going to use square root of x. You're going to use just u. And here you have du. Okay, very well. We have a nice formula to evaluate the integral of hyperbolic cosecant squared, which is equal to minus hyperbolic cotangent plus constant of integration. First of all, we have 2. We copy down 2 here, and here we have minus hyperbolic cotangent. And instead of having x, we have u. So let us copy down u here, plus constant of integration. But what is u? U is square root of x. We substitute that. Minus 2 hyperbolic cotangent square root of x plus constant of integration. Next example. Here you have definite integral 0 to ln of 3. Then we have hyperbolic sine raised to the third power times hyperbolic cosine x dx. Well, okay. So what do we have here? We have a function raised to an exponent. We have another function next to it. So when you have a function raised to an exponent, try to use u sum. See if you have the derivative of that function next to the function, so you can use u substitution and simplify your integral somehow. So let u be hyperbolic sine. What is du? We know that if you take the derivative of hyperbolic sine, it's equal to hyperbolic cosine. So let's take the derivative. Du is equal to hyperbolic cosine x dx. We're lucky in this case. Du is just right here. So your integral is now integral. First of all, since you're changing the variable, you cannot use previous lower limit and upper limits. For now, just leave it as blank. Then here you have sine, hyperbolic sine, which is u, so you get u cubed. And this guy is nothing but du. Well, this integral is easy to evaluate. Why is that? Because you have just the power function. This is equal to a 4, u to the 4 plus constant of integration. But what is u? U is hyperbolic sine. So this is a 4 hyperbolic sine raised to the 4, and it starts, the lower limit is 0 and the upper limit is ln of 3. So eventually you get plus minus constant of integration, and this guy is just 0. That's why when we have definite integral, we prefer not to write the constant of integration. Eventually, they cancel out. In the next step, we have to calculate the hyperbolic sign when x is ln of 3 and the hyperbolic sign when x is equal to 0. So this is equal to a 4. Let us use a bracket, hyperbolic sign. So let me write ln of 3 here for you, raised to the 4 minus the hyperbolic sign raised to the 4. And our goal is to calculate this. So let me erase this. Hyperbolic sign is defined e to the x minus e to minus x divided by 2. So when your x is ln of 3, you're just substituting ln of 3 for our x. So sine hyperbolic ln of 3 is e raised to ln of 3 minus e raised to negative ln of 3 divided by 2. Remember that e and ln, they are inverse of each other, so the composition is identity function. This guy is equal to, so sine hyperbolic ln of 3 is equal to e minus, let's cancel out this, we get 3 minus a third divided by 2. You can cancel out e and ln, and here if you flip this, you get 1 over e to ln of 3. You can cancel out e and ln, you get 1 over 3. So if you take common denominator on the numerator, you get 9 minus 1 divided by 3. The whole thing is divided by 2. So you get 8 divided by 6 or 4 thirds. This guy here is 4 over 3. Then you have to raise it to the 4th power. Now for sine hyperbolic, when x is equal to 0, here you have e to 0 minus 1 over e to 0. The whole thing is divided by 2. You get 1 minus 1 over 2, which is this. So this guy is 0 raised to the 4th power. 0 raised to anything is just 0. Here you're left with 1/4 times 4 over 3 raised to the 4th power, which is equal to, so you can cancel 1/4, 1/4, you get 4 to the 3rd, divided by 3 to the 4th, which is equal to 64 over 80. Some more integrals. More formulas. So if you take the integral of hyperbolic tangent x dx, it's actually ln of ln of, you don't need absolute value, hyperbolic cosine plus constant of integration. The integral of hyperbolic cotangent x dx is equal to ln of, for this case you need absolute value, hyperbolic sine x plus constant of integration. For hyperbolic secant, so hyperbolic secant x dx, we get inverse tangent. So inverse tangent, note that it's not hyperbolic tangent, it's just a tangent. Inverse tangent of hyperbolic sine x plus constant of integration. And finally, for cosecant, hyperbolic cosecant x dx, it's the inverse, okay? We don't need inverse here, it's just ln. ln of absolute value, hyperbolic tangent, x over 2, plus constant of integrations. Let's continue. So far we talked about hyperbolic functions. Now we're going to learn how to find the inverse of hyperbolic functions. Okay, inverse of hyperbolic functions. We are on page 5 of the note. So, suppose we want to find the inverse of hyperbolic sine x. How do we do that? So remember that to find the inverse of a function, we need to isolate x on one side and...
Excuse me, Professor. We don't have a clear picture again.
So our goal is to find the inverse of hyperbolic sine. So in general, to find inverse of any function, your goal is to isolate your independent variable x on one side. So let y be inverse of hyperbolic sine of variable x. So what's the meaning of that? It means that your x is equal to hyperbolic sine of variable y. Very well. How did we define hyperbolic sine? Remember that hyperbolic sine is defined this way. Hyperbolic sine in general is defined as e to the x minus e to negative x divided by 2. Now your variable is y. So it means that x is equal to e to y minus e to minus y divided by 2. So we use the definition of hyperbolic sine and we got rid of the hyperbolic sine and replaced that using exponential function. Now multiply both sides by 2, you get 2x equals to e to y minus e to minus y. Our goal is to solve this for variable y to be isolated on one side. So this is our goal. Isolate y on one side. It's all pure algebra. Guys, we don't have any calculus here. It's just all algebra. Very good. 2x is equal to e to the y minus 1 over e to the y. I multiply everything by e to y, so I get 2x e to y equals to e to 2y minus 1. What do I have here? I have e to 2y minus 1 minus 2x e to y equal to 0. Okay, perfect. So, what I'm going to do, I'm going to form a quadratic equation. Form a quadratic equation. How do I do that? E to the y is raised to the second power, so this is e to the y raised to the second power. Let me see, here I have -1, here it must be, this is -1, it should be, let me see. Very good. Okay, it's not a complete square, but eventually we can use quadratic formula to solve it. So e to the y raised to the second power minus 2x e to the y minus 1 equal to 0. Okay, so what do I have here? If you use a new variable like u, this guy is u squared minus 2xu minus 1 equal to 0. Remember quadratic equation and quadratic formula. If you have a, x squared plus bx plus c equal to 0, x can be solved using quadratic formula, negative b plus minus square root of b squared minus 4ac divided by 2a. This is the formula that you're going to use. Note that your variable is u. What is u? U is e to y. Okay, perfect. So, my u is equal to negative b. What is b? b is negative 2x. So, I have negative 2x plus minus square root of b squared, negative 2x squared, negative 2x squared minus 4ac. What is a? A is 1 and c is negative. The whole thing is divided by 2 times a, which is just 2. So my u, which is e to the y, is equal to negative times negative, positive. 2x plus minus square root of 4x squared plus 4 divided by 2. If you factor out 4, you can get rid of 2. So e to y is equal to x plus minus square root of x squared plus 1. So your y is equal to get rid of e, you take ln, y is defined as ln of x plus minus square root of x squared plus 1. So, inverse hyperbolic sine is ln of x plus minus square root of x squared plus 1. So we have more formulas. We can verify all of them using this method. Let me write some of them here for you. So far you learned that the inverse hyperbolic sine is equal to, let's see, ln of x plus square root of x squared plus 1. The inverse of hyperbolic cosine is equal to ln of x plus square root of x squared minus 1, and x must be between 0 to 1. 1 is included. Now you can follow this method to find the rest of the inverse of these hyperbolic functions. So how do we use these? Let us go over one example in page 6. In page 6, we have an example saying that
Larry again.
example says, find the points at which the function y equals to hyperbolic cosine x and line y equals to 5/3, so we have the constant function, intersect. Okay, first. So to find the point or points of intersection between these two functions, set them equal to each other. Set these functions equal. So we have hyperbolic cosine x equals to line 5/3. Then our goal is to solve for variable x. Now, solve for x. It means that we have to isolate x on one side. So x is equal to inverse hyperbolic cosine of 5/3. Very well. Do we have a nice formula for inverse hyperbolic cosine? Of course. It's equal to ln of x plus square root of x squared minus 1. So x is equal to ln of x is now 5/3 plus square root of 5/3 raised to 2 minus 1. The rest is algebra. You just need to simplify this and see what's going on. So x is equal to ln of 5/3 plus square root of 25/9 minus 1. So your x is equal to ln of 5/3 plus square root of, if you take common denominator here, 25 minus 9, which is 16. So your x is equal to ln of 5/3 plus square root of 16/9, and x is equal to ln of 5/3 plus 4/3, or x is ln of 9/3, or x is ln of 30. Okay. So take the inverse of hyperbolic cosine, they have to put x inside absolute value. Therefore, we get two possible solutions for our x, which is plus minus ln of 3. Well, so now that we define inverse hyperbolic sine, inverse hyperbolic cosine, we can take the derivative as well. So we learned that, we are on page 7. We learned that inverse hyperbolic sine of x is equal to ln of x plus square root of x squared plus 1. So now we can take the derivative of this function, new function. The derivative of inverse hyperbolic sine is equal to the derivative of ln. It means that you have to take the derivative of x plus square root of x squared plus 1 and divide it by x plus square root of x squared plus 1. This derivative is equal to, so the derivative of x is 1, the derivative of square root of x squared plus 2x is 2x divided by 2 times square root of x squared plus 1. The whole thing is divided by the denominator, which is x plus square root of x squared plus 1. The rest is just algebra. Here you can cancel out 2 and 2. You get on the numerator square root of x squared plus 1 divided by x squared plus 1 inside the radical plus x divided by square root of x squared plus 1. On the denominator you have x plus square root of x squared plus 1. Now on the numerator you can take the common denominator between these two. Okay, square root of x squared plus 1 plus x divided by square root of x squared plus 1 over x plus square root of x squared plus 1. Okay, of course we can simplify this. Here you can cancel out x squared plus 1 inside the radical plus x and x squared plus 1 inside the radical plus x. So the outcome is equal to 1 divided by 1 over square root of x squared plus 1. That's the derivative of inverse hyperbolic sine of x. Okay, with the same method, we can take the derivative of hyperbolic, inverse hyperbolic cosine. 0 and 1. So the derivative of inverse hyperbolic cosine is equal to the derivative of ln. So here you have to take the derivative of x plus square root of x squared minus 1 divided by x plus square root of x squared minus 1. This is equal to, so the derivative of x is 1, the derivative of the quantity inside the radical is 2x divided by 2 times square root of x squared minus 1. The whole thing is divided by x plus square root of x squared minus 1. So of course you can cancel out 2 and 2. You can take the common denominator between these two. Here you get square root of x squared minus 1 divided by square root of x squared minus 1 plus x over square root of x squared minus 1. The whole thing is divided by x plus square root of x squared minus 1. So on your numerator, now you have just square root of x squared minus 1 plus x divided by the common denominator, which is square root of x squared minus 1. Everything is divided by x plus square root of x squared minus 1. So, of course, you can cancel out the numerators because they are the same. This numerator are the same, so you can cancel them out. The alpha is equal to 1 divided by square root of x squared minus 1.